Hello everyone, welcome to our channel. And last time I built the circuit. We have this, a touch switch. Also we have here a timer switch. And then we have this, a tone generator or LED flasher at the same time. Also we have here a 4-bit counter. And then we also have this, a constant current source toy module. So we have 5 toy module, and now we have this. This is a toy module, a transistor bistable multivibrator. We have the output LED, input LED, power LED, PNP transistor, switch, push button, NPN transistor, some resistors, also resistor here, a resistor there, and we have the jumper settings. Also here, a jumper settings. And the base, we have the input, output, and power header. So this is a transistor bistable multivibrator. So let us power on the circuit. Now the power on LED turns on, and then this is the case of designing, constructing of bistable multivibrator using a simple circuit, and the output goes like this. Did you see the light? So let us first check if this works as a bistable multivibrator. Push the switch. The other one. It latches. Another. It's a flip-flip. But the problem with this setup, this mode, is there's a little light in the other LED, other output LED. That is the question of the problem. We always encountered with that problem because that is the conductance or transconductance developed in the transistor. It seems that because when we're designing the RS flip-flop or this RS latch or bistable multivibrator, we are dealing with latching the switch or the output, but there's a little light here. So we need to modify the circuit using this mode. Let us see now again. Using the PNP as a current source, we now have this. So we're now using 4 transistor. Before we are using 2 transistor. Now we are using now a 4 transistor. 2 NPN and 2 PNP. And now this is the output. This is the full build circuit of a transistor bistable multivibrator with one output LED turns on every time you push the switch. The other one, it latches. It toggles, it latches or toggles or switching to the other side of the light. That is the characteristics of bistable multivibrator. And now, as you have seen here, LED is fully turned off because of the transistor PNP that served as a constant current source to the circuit. So every time I push the switch here, input LED turns on, and this is displayable. Once you have done with the project, you can now display this in your display cabinet as a souvenir that you have already built a circuit called Bistable Multivibrator, or it's sometimes called RS latch or RS flip-flop. And this is the full build circuit, a toy module. So to understand what's happening here, aside from the other features, we have the input-output provision here. We have the input as a switch here, also for the output provision. But we are interested on how to design the circuit with the use of using a simple and a modified circuit version of this Bistable Multivibrator. So let us now see how the design, what is the design of the circuit, by looking to our circuit diagram here. This is now the simple Bistable Multivibrator, sometimes called RS flip-flop, that stores 1 bit of memory. Bistable Multivibrator, RS latch, sometimes called, it holds 2 states, either 0 or 1, and it is a computer 1 bit of memory, or 1 bit computer. And this is the circuit diagram. We have 9-volt supply, and that is the transistor configuration, circuit configuration. We have the switch, input LED here, output LED, now the power on LED. So when you, let us see again the setup. This is the setup of the first circuit, of the first diagram. Turn on. So once you turn on the circuit, we're going to compute for the values of all the resistor here. And once you turn on the circuit, this is the stable state of the circuit. The other transistor is on and the other is off once you turn on the power, and power LED turns on, as you have seen here. The other one is on, and with a little light here, that is the problem, or the problem of this circuit, and we're going to see. So we're going to take the KBL here across the R1 and D5. So first we have here a given diode rating 0.02 at the data sheet, voltage drop 2 volts, no data sheet of the LED, the collector emitter at saturation. So we're going to use transistor in saturation mode. 0.3 Q1, 0.7 IB, voltage D4, ID4. We have here 2 volts diode and HFE of 100. That is the given according to the data sheet of the LED and the transistor. We're going to find here all the values of the resistor. So Q1 on at the initial state due to the doping properties of the transistor. So that is the initial state once you power on the circuit. Due to the doping characteristic of the transistor, one of the transistor is on, the other one is off. But in theory, it should be both are on. But in real world, due to the different doping characteristics of the transistor. The other one is on and the other one is off. So let us now power LED on. So using KVL here, we're going to compute for the value of R1, BCC, voltage drop R1, voltage drop at D5. Transposition using KVL, computation 9 volts, voltage supply, voltage drop of the diode or LED 2 volts. We got now 7 volts voltage drop across the R1. Using Ohm's law, we get here, since we know that 7.02, that is the current at R1 is equal to the current at I5. Since they're series, we're now going to have here 350 ohms, but I use 70 ohms available resistor. So R1 now here is 470. Since Q1 is on at the output side, so we're going to take a KVL at the output side. BCC minus voltage drop RC1, D1, CE to the ground. BCC, that is the KVL, Kirchhoff's voltage law. Transposition, substitution, since we know this in the datasheet transistor, we got 6.7 volts voltage drop across RC1. Also, the current flows here into the input side due to the initial stable state of the transistor. So we're going to have here. But since we know RC1, the voltage drop 6.7, using Ohm's law, we got now the value of RC1, 6.7.02, 470. The current at RC1 is equal to the current rating of the LED since they are in series. So we are now here at the input side. So we're going to compute for the values of RB2 and RC2. RC2 is equal to RC1 because we're going to design a stable circuit. Once you know RC1, you know now the RC2. They should be equal. And this value of RB2 we're now going to compute. We have to know the current flows that flows here at the RB2. So using current gain, HAP of the Q1 here. And then substitution, we got now IRC1 0.002. I'm using HAP or beta of 100. That is now the current that flows at the RB2. KVL now at BCC to base emitter. BCC to turn on the transistor, since this is the initial state, transistor 1 is on. BCC minus the voltage drop RC2, D4, RB2, and base to emitter at saturation. Substitution here using KVL. We get now this equation, 6.3 volts. So at this state, RC2 is equal to IB2. We are now going to use IB2. RC2, current at RC2 is equal to the current at RB2 since they are in series. So let us now use Ohm's law and substitute that IR into equation 1. Since IB2, RB2, RC2, current is equal, substitution 6.3, and then simplifying, we got now here 470, we got now here RB2 is 31,030 ohms. Since here we know the values of the current and the RC2 here, just substitution, and we get 31,030 ohms. Now we know the value of R1, RC2, RB2, RC1, and let us now see what happened to the next state. We are going to trigger a pulse here at RC2. Let us trigger the pulse here. What happened is LED toggles, or I mean latches to the output. So once you push the button here, the other LED turns on, as you have seen here. So we're going now, since we know now only 3 resistors are unknown. So this state, Q2 now is on, Q1 is off, as you have seen here. Once you apply a triggering pulse, reset button, current flows to the BCC, since we know that already, RC2, D4, CE SAT. Also current flows here, RC1, D2, RB1 to BE to the ground. Applying triggering pulse here using KBL, BCC to Q2. So applying KBL here to Q2. This is the input side. And then BCC minus voltage drop, RC2. Oh no, this is not an input side, this is the output side. Let us see the output side. Since this is turning on, BCC, more voltage drop, BC2 minus voltage drop at D4, and then collector to emitter to the ground of the Q2. The BR2, where is that? Here. BCE2, RC1. So let us see what happened here. Oh, applying a trigger pulse. This is another the current flows here also when you apply a pulse here to the BCC, BR2, BD2, and to the base of the emitter. So in order to compute for the values of R2 here, applying KBL, BCC minus BR2, BR2, BD2 minus voltage to emitter of the transistor here. Substitution, since you know all the values, 6.3 volts across R2. Using Ohm's law, substitution, we got 315 ohms, but I use 470 ohms. That is the case of applying a positive triggering pulse. Since this type of circuit configuration is a high level sensitive. Applying the pulse here, this LED output turns on. So now here we know the values of R2. Now let us see Q2 on. So Q2 on and KBL at BCC to base emitter. So we're going to make a KBL here to forward bias the transistor here, since we know that this is on. BCC, voltage drop RC1, D1, RB1, base emitter, saturation. And then we got this equation. Voltage at RC1 plus RB1 is equal to 6.3 volts. Now this is our first equation with this KBL. To compute for the current at the RB1, we're going to use the transistor current gain, HFE IC over IB, since our IC here is IRC1, IB is IRB1, using 100 SAHP, we have current at RB1 0.0002 ampere in this input side. Since RB1 IC1 is equal to IB1, we get 0.002 ampere in this state. Using Ohm's law, substitute the IR in terms of IR. Since they are in series, current here is equal to the current to the RB1, same current. Substitution, we got now here, since we know the values, all 31,030, the same as the RB2. Same computation. Now, this is now the values of the resistor. Now, when I push the button here, it toggles or it latches to the other side. So this one now is on. So it means current flows here, there, and here. Since we know all the values except for this one, we're going to take KVL here, BCC minus BR3, BD3 to the base emitter. Since we know all the values, 6.3 volts, Ohm's law, we got 470 ohms. Now we have now all the values of the resistor. By pushing the switch, we know the values, computing the values, and we get this. But the problem with this circuit is this. There's a little light. The LED is not fully turning off. That is the case of this simple circuit of a bistable. That is the properties of the transistor. It develops a conductance or transconductance, and the output LED is not fully turned off. So in here we have, this is active high or normally high level sensitive, this type of circuit. And this is the timing diagram. Once the set button, or this one, is on, reset, even you push it again and again, nothing happens here. It will not change the state, because here every time you push it, nothing happens. The Q or the output is still on. That is the output Q, unless you are using this another switch, a reset. This is the reset switch. Let us now, it toggles or it latches. So now the output is 0. The Q, and this is now the Q net. This is the timing diagram. That is the case of our circuit. Once you push it in here, LED latches the output. That is the characteristics of the bistable. And this has an equivalent circuit here, an OR gate, RS, just like this one, RS, NOR gate, Q and Q complement, or Q bar or Q naught. Did you see here, the input is coupled to the output, just like this one. The input is coupled to the output of the other transistor. So the circuit, the equivalent logic gate is this, an OR gate, and this is the block diagram. So this one is, oh, I forgot this one, should be 0 here. This is the block diagram of RS, latch, should be 0 here, 0. When S is 1, the Q is 1. When S is 0, the Q is 0. Reset the complement. When 0, you're going to reset that, becomes 1. reset 1. When you reset that, 0. That is the block diagram of the Bistable Multivibrator, the same as the RS flip-flop or RS latch, the same as this NOR gate equivalent circuit. All in all, they bought all the same. That is the summary. So that is the problem of the output LED. So we're going to modify the circuit using the PNP current source, constant current source, by sliding the jumper here. As you have seen here, we get now a good circuit here. The output LED is fully turned on and off, changing its state from 0 to 1, and we have a good light here. This is the case of modifying the circuit, and we are now here. This is the modification in order to have a good LED output by connecting a PNP. Now the LED is in here with the PNP using 2N3906, which is complement to the 2N3904. Before, our LED, we put the LED in here. Now it's here, providing a constant current source to the LED. And now the transistor conductance or transconductance developed will no longer appear. And because of that, we're going to compute for the values of the resistor here from our new circuit. And this is now our new circuit using the PNP as a constant current source. We got this new lights or good lights to our module. We're going to compute for the 4 values of the resistor. We are all have the given here. Collector emitter, all HFE, HFP, BCE, BBE, all in the data sheet of the transistor. Q3 is PNP, Q4 is PNP, Q1 NPN, Q2 NPN. So we get 2 PNP, 2 NPN transistor. And find the values of the 4 new resistor. As solution to the output side. Okay, we are going to use the current gain formula of the Q3. Current gain formula here, and we get HFP IC over IB. IC now, as you have seen here, IC is equal to IE, since we're going to use transistor in saturation mode. IC is equal to IE. Since this is IE and this is IC, emitter, base, collector, is equal. IE equal to IC. Substituting that, and we know that that is 0.02. That is the required load current to turn on the LED. We're using HFP. We got now the base current at the RB3, or equal to the current at the Q3 or transistor Q3. So we now know the base current using the current gain, and now we're going to, at the output side, BCC to BC. BCC, BR4, BD1, BCC minus BRD minus BD1 minus collector to emitter or emitter to collector. That is the second KBL of the output. Using the KBL there, we get 6.75 volts. KVL to the ground. And using Ohm's law, since we know all the values here, voltage at R4 is 6.75 and the current is 0.02. Now we know the value of R4 here, which is 335. So I use 470, my available resistor. And now we have here KVL BCC to RC1 to QC1. RC1 to QC1. Also current flows here. This is on, this is off. So current flows here, also here. BCC minus BRC1 and B collector to emitter. And we get the voltage at RC1 equal to 8.7 volts. Since Q3 is pushing current here, voltage RC1 is equal to voltage BE at the Q3 plus voltage RB3 at the Q3. So, voltage at the RC1 is equal to the voltage at the base emitter plus the voltage at RB3. This is a pushing current. The voltage here plus here is equal to RC1. That is our new equation here. So we got 8.05 volts using Ohm's law, and we know the voltage drop and the current at the base, we know that. We got now here 40,250. I use 40K available resistor. Since this is symmetric, it means R4 is equal to R5. RB3 is equal to RB4. That is the case of symmetric circuit. So we got now here. So this is now my schematic diagram using the header, the power header, jumper. When I'm going to use without PNP, I just slide the header connecting this line to here. Without this, just connect it by a header or by the jumper, or if I'm going to use with PNP, the PNP transistor, just slide the jumper here. We're going to connect here and here, same as the other side. If you plan to connect only the output, simple bistable multivibrator, just connect this B to C through jumper settings. That's why. And then we have this this switch. We also have a switch provision here, and also we have an output. We can connect an output LED here by patching here DC, and we get the power supply here. So every time I change the jumper settings, that is in our jumper settings here, by sliding the jumper ABCD, and we have here, I'm using this layout. So that's the operation of our new module, toy module, a full build transistor bistable multivibrator. And this is displayable, and once you have done with the project, you can now display this as a souvenir that you constructed a transistor bistable multivibrator, or sometimes called RS flip-flop, or SR LUTs, or SR flip-flop, or RS flip-flop, that can store 1 bit of memory, and it has 2 stable states, 1 or 0. I should push the switch here. LED toggles. Okay, now Thank you for watching and bye bye.